Good evening and welcome to another corny video by yours truly. Let's try to get through this as quick and painless as possible. First, let's talk about square roots. Square roots are just the inverse of squaring. Just like subtractions, the inverse of addition, and divisions, the inverse of multiplication. Squares also have its inverse. I'll give you an example. Square root of 25 equals 5 if and only if 5 squared equals 25. They go hand in hand. However, we'll go with another one. It's not the only one. So square root of 25 also equals negative 5. Why? Because the negative 5 squared equals 25. So what that means is that the square root of 25 gives us plus or minus 5. We've been dealing solely with just the positive root and not the negative root, because the actual positive root, that one right there, is actually what we call the principal square root. And that's what we've been mainly dealing with. What you'll notice is that every square root has two real roots. I'll give you an example. Square root of 9, not just 3, is actually plus or minus 3. Square root of 1/9 is not just 1/3, it's actually plus or minus 1/3. The square root of 9/100 is not just 3/10, it's actually plus or minus 3/10. So let's move forward so we can see more. One rule you'll get is that the square of a real number is never negative. So you'll never ever square a number like a negative number and get a negative number. It'll always turn into positive. So looking at this right here, if you look at this equation, x squared equals b, if in fact b is negative, you won't get no solution. What you'll have to actually put is no real solutions. There are solutions to it, but we'll get to those a lot later. So what you'll get from that is that a negative number has no real square roots. You can't take the square root of a negative number. Go through some examples with this. X squared equals 9. If I want to solve this, for the most part, I take the square root of both sides. And if I take the square root of both sides, I'll get x on one side and plus or minus 3 on the other. All right. So the roots of this is just going to be 3 and negative 3. If I go with x squared plus 4, remember, solving for x, I'm going to take 4 to the other side and then take the square root of both sides. If I do that, I'll get x on one side, but the square root of negative 4 on the other. So what that means is that there are no real roots to this equation. One more, if you have 5x squared equals 15, divide both sides by 5, you'll get x squared equals 3. Take the square root of both, and you will get x equals plus or minus the square root of 3. So the roots of this equation is going to be square root of 3 and negative square root of 3. If we keep on going with other roots, let's talk about cube roots. Cube roots have one root. Example, you have the cube root of 8. It's just going to be 2, not negative 2, because negative 2 cubed does not give you 8. Here, if you have the cube root of negative 27, you're going to get negative 3, not 3. Because if you cube 3, you're not going to get negative 27. Here, this is going to be 10 squared, because if in fact you did cube 10 squared, you'll get 10 to the 6th. And if you took the cube root of 8 to the 9th, you should get 8 to the 3rd. We'll do a lot more of those later. So about nth roots. Nth roots are basically the roots that are, when we talk about nth roots, we're talking about roots bigger than squares and cubes, even though those are nth roots themselves. Notice here we have a 5, we have a 6, and we have a 9. That's what I mean by nth root. So this is the 5th root, 6th root, 9th root. That's what I meant like when I want to generalize them and stuff. Another rule that I want to give you is if in fact n is even, so if in fact our root is even and our radicand is positive, then we have two real roots. It's just like square roots, exactly like square roots. So say for example the 6th root of 64 is going to give you plus or minus 2. Why two roots? Because our root is even. Here, if we take the 4th root of 625, that's going to be plus or minus 5. because we have an even root. So let's go on to other roots. To give you another rule, if in fact our root is even and our radicand is negative, then we have no real nth roots. It's the same exact thing as square roots. They have the same rules to them. For example, square root of negative 16, no real roots. Or so you can put no real solutions or no real roots, I don't care. If you have the fourth root of negative 256, no real roots. So you can put no real roots or no real solutions, whichever one you would like to write. Another rule is if n is odd and the radicand is positive, then there's only one real nth root. We saw that with cube roots, right? So for example, here you said the fifth root of 32. If you take the fifth root of 32, you should get just 2. Not plus or minus 2, but just 2, because our root is odd. However, we took the fifth root of negative 32. Guess what we're going to get? Negative 2. Because if you took 2 to the fifth, you'll get 32. If you took negative 2 to the fifth, you'll get negative 32. Once again, we'll do more of those in class as we go. Those are the properties of a radical and what the small components are, the vocabulary that we'll actually be using. We'll go further in those a little bit more. We actually get 2 rules from this. One rule, this looks like a whole bunch of gibberish to understand, but for the most part all it says is that this nth root cancels with the n exponent. So the nth root of b to the n is equal to b. I'll give you an example of what I'm talking about. The cube root of 12 cubed. The cube root cancels with the cube. So my answer is just 12. Another example is the square root of 7 squared. Square root cancels with the square. My answer is just 7. Also, the second rule is kind of just like it. If in fact the exponent's under the radical, that's the same as the root. They still cancel. So that means the nth root of b to the n is equal to b. 2 examples. First one, fifth root of 10 to the fifth. Fifth, cancel with the 5, 10. Next one, fourth root of 5 to the fourth. That cancels with that, 5. Period. Couple more properties we want to actually go through just so we are better understand this stuff. If you take the square root of 4 times 9, that's the same thing as the square root of 36, which is just 6, right? If we take the square root of 4 times the square root of 9, you get 2 times 3, which is also 6. So what you can deduce from that is that the square root of 4 times 9 gives you the same thing as the square root of 4 times the square root of 9. So that means they're equal, right? That yields a rule. Before that rule, you also see similarly, if you go through the motions, you'll see that the square root of 4 over 9 equals the square root of 4 over the square root of 9. The rule we get from that is that you can break numbers up or terms up under the radical into 2 separate radicals through multiplication and division. That's the rules that you actually get from that. Never, do not do this. So you cannot break up an addition problem. You can only break up multiplication problems and division problems. You cannot break up addition problems or subtraction problems for that. Example of this. Is that a true statement? This is going to be the square root of 25, and this is going to be 3 plus 4. Now, does 5 equal 7? No. So that does not work. It only works for multiplication and division. Let's go a little bit further so I can give you examples. Say if in fact I wanted to break apart the square root of 98. Let's break apart 98. You want to look for the factor that's a perfect square. The factor that's a perfect square inside of 98 is 49. So if I split it up into 49 times 2, I can split that up even further into 2 separate radicals. The 2 separate radicals, the square root of 49 and the square root of 2, right? So from here, we all know what the square root of 49 is. It's 7, so my answer will just be 7 times the square root of 2. Same thing with the square root of 2a squared b. I can break that up looking for the perfect square. Looking at that, the perfect square is a squared. So I get that by itself to be the square root of a squared times the square root of 2b. And from here, the square root of a squared, remember what I said, this cancels with that. So what I'm just going to end up with is a times the square root of 2b. If in fact I have a multiplication problem, it's the same idea. I'm going to put it together, then split it back up apart to get the perfect square out. So if I'm getting the perfect square out, you have the square root of 18 times 6 is what I get from our initial problem. And that gives me the square root of 108. Now, I have to ask myself, is there a perfect square in there somewhere? There actually is. I'll take the square root of 36 times 3. Now, since I have the square root broken up out of the 108, I can split it up in separate radicals. And notice the square root of 36 is just 6. So my answer is just 6 times the square root of 3. That's all I need to do to simplify each one of these. So what I want you to do now is I want you to take these two problems right here, and I just want you to simplify them. So pause the video, simplify these, and then replay the video to see if in fact our answers match up. So pause the video right now. Is this what you got for your answers? I hope so. Notice what I did for the first one. For the first one, I was seeking the perfect square out. So what I got out of 18m cubed is 9m squared, and what's left over is 2m. So from there, I broke it up into the square root of 9m squared times the square root of 2m. And then the square root of 9m squared is just 3m, so I get 3m times the square root of 2m. With the square root of 24 times the square root of 8, if I combine those, I get the square root of 192. And then I can break it up again after that to get the square root of 64 times 3. There's my perfect square. After I get that perfect square out, I separate it into radicals. Square root of 64 is 4, and the square root of 3 just stays that, so I end up with 4 times the square root of 3. So let's move on from there. To rationalize the denominator, we're going to be doing a lot of this as we move forward, so it's very, very easy once you get used to it. First things first, we do not want a fraction under our radical. What that means is if you have a problem that looks like this, the square root of 5 over 3, we don't want a fraction, so we do whatever we can to get rid of it. Now what we want to do is multiply by some variation of 1 to get rid of fraction in our radical. The variation of 1, why not 3 over 3? Let's see what happens when we do that. If we multiply by 3 over 3, see what it does to our denominator here. The top is going to be 15, the bottom is going to be 9. Now, remember what the rule was. I can split that up. Since it's a division problem, I can split that up into square root of 15 divided by the square root of 9. And now the square root of 9 is just 3, so I get the square root of 15 over 3. The second view is we don't want a radical in our denominator. You can see it this way. If I take, say, 4 over the square root of 2, we never want a radical in our denominator. So what we do is we rationalize it. We do the same exact thing. Multiply by some variation of 1, which is, in this case, the square root of 2 over the square root of 2. So you really just take... it's kind of like you multiply by an LCD. Whatever you do to the bottom, got to do to the top kind of thing. So it's going to rationalize the denominator. And what happens there is you're going to get 4 times the square root of 2 over the square root of 4. Remember what the square root of 4 is? Just 2, right? So I end up here. And if I'm fully simplifying this, that cancels out. This becomes a 2, right? So that means our answer is going to be 2 times the square root of 2. That's the idea behind rationalizing the denominator. So I want you to pause the video again and try these two problems and see if in fact it matches up to my answers. So pause the video now. This is what I got. Note to rationalize the denominator. Notice my denominator is 5, so I just multiply by 5 over 5. To get the square root of 10 over 25, I can split that up to be square root of 10 over the square root of 25. And that's going to give me the square root of 10 over 5. And I'm done right here. with this one right here, I want to rationalize the denominator. I want to get my denominator to not be a radical, so I'm going to multiply that by the square root of 5. And whatever I do to the bottom, I got to do to the top. So what that gives me is 10 times the square root of 5 over the square root of 25, which gives me 10 times the square root of 5 over 5. And I cancel that out to get a 2. Final answer, 2 times the square root of 5. We'll do a lot more of these in class. This is the end of this corny video. See you later.